All right, I'm gonna go ahead and get started, guys. Here we go. I'm Sarthak. I'm gonna be leading this presentation today. Um, I'll just give a quick recap, a quick introduction of who I am. But I've been the software lead on Wizards.exe, FTC Team 9794 for the last 5 competition seasons. And in this presentation, we're going to explore the different programming options available to FTC teams, and in particular, within those options, explore some of the powers block programming has and how it can really kind of change the dynamic of your team. And after discussing the programming options, I'm going to walk through some examples of advanced sensor implementations that will help your team take your software development and, in the process, your robot performance to the next level. This presentation introduces the key points and high level understandings of these topics. And throughout the presentation, I'll be making references to our already published training materials that further expand on those ideas. This presentation was pre recorded for the World Shop FTC conference that happened a couple weeks ago. The presentation lasts about 45 minutes. And after that, I'll be around to take any questions that you guys have. If you do have questions during the presentation, you can type them in the chat. Just a fair warning, the presentation's on a 30-second delay, so there might be some time in between when you ask your question and when it gets answered. But I'm going to go ahead and start the presentation. If you guys have any questions, just type them in the chat, and I'll get back to you as soon as possible, I guess. But here we go. And if there are any problems with the audio or video during the presentation, please be sure to let me know and I'll try and fix it as fast as possible. Thanks. Hello, everyone, and welcome to the Advanced Programming presentation and section of the World Shop International FTC Conference. I'm very excited to share some of my experiences with you guys and introduce some key concepts that can really take your programming and your robot software to that next level. So my name is Sarthak, and I've been the software lead on FTC Team 9794 Wizards.exe for the last 5 years. And so I'm just going to share some of my experiences with you guys, some of my expertise, and hopefully you can apply that on your own robot and in your team to really help improve your robot performance going forward. Now, just before I start the content of this presentation, I just want to give a quick introduction to my team. So as I said before, I'm on FTC Team 9794 Wizards.exe, and we're a fifth-year robotics team from Rockville, Maryland. 2 years ago, we won the Inspire Award at the Detroit World Championship, the FTC World Championship, and our team's mission is to engage, expand, and educate different communities to promote STEM and FIRST through our various outreach and training programs, just like this World Shop International FTC conference. Now, before we really delve into the details of our presentation, I just want to briefly talk about the high level concepts that we're going to cover today. This presentation will be, I'm guessing, around 30 to 45 minutes long. We'll see how it turns out, but that's my ballpark for the presentation. And we're going to discuss two main areas: programming options in FTC and some advanced concepts involving sensor fusion and advanced sensor integration. Both of these areas are very key to having a strong grasp on the FTC programming system and being able to develop advanced software. I will talk about the three programming options available to teams, and specifically, we're going to explore the power of block programming and how it can really transform your team, just as how it has transformed my team, Wizards.exe. And then following that section, we're going to move into the sensor fusion and advanced sensor integration section, where we're going to discuss and talk about why sensors are so important for your robot, common applications and common sensors that FTC teams use, and then taking the next step to go to advanced implementations and features to really take your robot's performance and your software development to the next level. So it's key to understand the different role that your programming language and how you implement different hardware and electronics to really take your programming from a more common or basic level to really the next step to get to the advanced programming level. So now we're going to start out with programming options. So you may be familiar with all three of these options, but I'm just going to walk through them. So we have three options available to FTC teams. The first is the block programming language, which is a simple drag and drop software, similar to Scratch if you've used that, but you use that simple drag and drop software to program your robot. You can use this for autonomous, for teleop, for anything. I'm going to talk about this a little later, but block programming, it's has a lot more power than people think it is, but we'll get into that in a little bit. The second option is on Java, which is kind of that Java environment built into the phone. And the main purpose is that it reduces the compile time. Just like blocks, it only takes blocks is instantaneous to save programs on your phone. On Java, from my experience, takes 3 to 5 seconds um, to compile your code onto the phone. And the third option is Android Studio. So in Android Studio, you use Java to program the FTC application, the app that you download off of your robot controller. But you program the FTC app, make your programs on there. And Android Studio also offers the added benefit of being able to import external libraries into your software. But we'll get into all that a little later in the presentation. But those are your three options available to you guys. I personally have a lot of experience with block programming and Android Studio, and they're both very powerful, both very useful for lots of different applications. So why don't we get into that? I'm just going to briefly discuss the block environment versus Java. So as I mentioned before, we have a graphical programming language interface that is uh, block programming. Simple drag and drop. You can see the different types of blocks you have here. You can run your programs in here, all of that. And the only really application that's required is Google Chrome. And or any really Google Chrome is recommended, but any internet browser works just fine. So that's really important to notice. I'm just going to hide the webcam so you guys can just see all the text real quick. And we have Java, which, as you probably know, is a text-based programming language. It requires some more background information. Generally, you should have a background information in any programming language, just the structure, object-oriented programming. And if you know one programming language, the syntax is relatively easy to learn for Java. But if you're starting from scratch, there's a relatively difficult learning curve in terms of acquiring the knowledge of the syntax, naming conventions, etc., that's required to program in Java. And then you can use onbot Java, like we discussed in the previous slide, but the most common way of using Java in FTC is through Android Studio. Android Studio requires a decent amount of processing power on your laptop. It's a tedious installation process, often with many complications. And then you're probably going to want to use GitHub, which is a version control software. We're not going to talk about GitHub and Git in this presentation, but if you would like to learn more about how you can use that in FTC, uh, please feel free to go on our YouTube channel, search up version control, and you'll learn how you can use GitHub and Git in your software. But that's not going to be covered in this presentation. Just wanted to give you that heads up. So, just I'm gonna start out with some disadvantages to block programming. Um, you can't use external libraries, for example, OpenCV, which is a vision library, Roadrunner, which is a motion profiling library. We're actually going to talk about both of these in our presentation later on. So just it's good that I was able to name drop them there, but just keep an eye on those. But you're not able to use any custom sensors that are outside of kind of the default I2C configuration. There's no object-oriented workflow, so you can't really create any hierarchies or structures there. And the code can look like a mess when it gets really long. It's a little difficult user interface to use when you got a lot of code building up. But there are functions just like in Java in order to clean up the code. Um, and really, only teams that want to make advanced software kind of need these things. They need object-oriented workflows. They need custom I2C sensors. They need external libraries like OpenCV and Roadrunner. Um, and when we're just starting out, we don't really need these things, and this is why block programming is so powerful. You can make autonomous programs in this language. In fact, in 2016, our first few competitions, we used block programming to run our autonomous, and we were this was in Rail Recovery, and we still had a perfect autonomous there. It's very useful for prototyping. Just you can instead of having your programmers just build up, having to have your programmers test out your different prototypes on the hardware. Um, you guys can make your own programs to briefly test motors, servos, sensors, those type of things. Since it's real simple and everyone is able to use it, it's very easy to learn as well. Um, which is really the big advantage. And until you need to get to the point to import libraries, create custom sensors, use object-oriented workflows, You should stick to block program. I think you can still use sensors. We developed a really great guide. It was targeted towards first global teams, but really any team can use it. You can see over here. Scan this QR code. We have some basic videos walking through the basics and fundamentals of block programming, and really shows you a lot of things are possible. You can make perfect autonomous programs. You can make really great driver controlled programs. It's all about those videos are all about how you can use block programming, and really the only limitations are taking that advanced step that we're actually going to talk about right now. So I really encourage you guys to check it out. Don't be scared or don't be timid to use block programming because you want to use Java. You think Java's cool. Block programming is just as good, just as efficient, just as powerful. Um, so go ahead, check out those videos if you guys want to learn more about block programming. But now we're going to move on to kind of the key point of this presentation. We want you guys to be able to take that next step into advanced programming. And a lot of that revolves around using different sensors together. That's what we call sensor fusion, and kind of advanced applications of those sensors in themselves. And that's really important for developing robots that have really great autonomous programs going above the basic things. But like in this year's game, you want to get a 4 stone or a 5 stone autonomous, you need sensors for that. You need advanced sensor integration. You need some of the libraries we're going to talk about. You want great teleop programs that make it really easy for the drivers to drive the robot. That requires sensors, that requires a lot of advanced things. So we're just going to briefly cover several of these high level topics, some of these sensors that you may want to use, and really help you take your robot's performance to the next level with advanced programming. So why don't we go ahead and get jump in? So I just touched on this, but the first step to advanced programming is sensors. Sensors allow the robots to be more aware. You can make decisions and react to in-game scenarios that you might be able not be able to predict. What happens if your robot hits another robot and veers off course? What happens if you run into the sky bridge, for example, in this year's game? How do you recover from that? Sensors allow your robot to make those decisions in real time because there are things that you're not going to be able to guess or predict that are going to happen on the competition field. And using these sensors and being able to use them properly leads to a much more consistent and reliable autonomous performance. And I think being able to use lots of sensors on your robot adds a lot more intelligence to your robot. I'm just thinking to last year or 2 years ago, my team personally, we used 20 different sensors on our robot, and we had a really great autonomous performance. And I think the really key difference between our team and other teams was how much we're able to use sensors in our teleop period, because that's what really separates the good teams from the great teams, the middle tier from the top tier. You got to be able to drive really quickly, drive really fast. Sensors will allow your robot to automate some of the difficult processes um, through driver controlled enhancements. And we're going to talk about that towards the end of the presentation. But I kind of just really want to get this key concept in your mind that sensors are the key for you to be able to elevate your robot, elevate your software to that next level. So, the premise or the basic starting point, I guess, for sensor applications in FTC is kind of bringing together a bunch of simple sensors. So you got motor encoders, you have ultrasonic or distance sensors, IMU, gyro sensors, color sensors. There are a lot more other sensors in FTC if you get my drift. But bringing those sensors together is very important. I'll just bring up one example. In autonomous this year, you can use motor encoders to move to different positions, drive straight 24 inches, pivot 90 degrees. If you want to pivot 90 degrees, you can use encoders, or you can also use your gyro sensor right over here. That'll give you a absolute frame of reference to pivot. It will make sure that if your encoders drift, your pivots aren't gonna go awry, and you're gonna drive across the field or get penalties, all that stuff. You have to be able to use different sensors together to get a really consistent and reliable performance. Another example is if you're primarily using motor encoders to move. Motor encoders have slippage. That's just a reality you have to deal with because your drive wheels, what if they run into something? They're going to slip. What if you're pulling the foundation in this year's game, but the foundation has a lot of friction and your wheels are just spinning? You could go for time, but that's not really the most effective way to do things. Ultrasonic sensors give you the option to measure distance from your robot to a fixed point of reference, like the perimeter. for example. So you can always measure your robot's position in real time. And that kind of takes you from relying on just one set of sensors to bringing together different sensors to allow for redundancy, and just really, in general, consistency and an overall rise in reliability, which is really important for your FTC performance, since autonomous is usually a really key component. You have to be able to have a really consistent and reliable autonomous, and bringing together different sensors is a really key aspect of that. I just mentioned this. Our team used 20 sensors over the last 2 seasons in a single year. There are lots of ways you can use sensors. There are lots of ways you can implement them to really make your robot more consistent and reliable. And then, kind of going from that next step, just from the simple sensors, is you want to cover some more advanced things. So we have vision systems. You can use your phone camera. You can use a web camera, like the ones you would use to Skype call, or the one I'm using to record this presentation. But vision systems are really key. And this year, you have to identify that skystone target. In previous years, you've had to identify game. Sorry, excuse me. You've had to identify game elements or. Hello, everyone, and welcome to the advanced programming presentation. Hey guys, something just malfunctioned with the video. Just give me a couple seconds to fix it up. I'm gonna try and bring it to roughly where it was in the beginning, so there might be some repeating of information, but I'll try and fix that as quickly as possible. So you guys will just have to give me a second, and I'll try and bring it back. Hello, everyone, and welcome to the advanced programming. There are lots of ways you can use it. So we have vision systems or. All right, I'm gonna try resuming it from right here, and hopefully it doesn't happen again. There again might be some repeating information, but here we go. Robot, I'm just saying this because you can do this. You can put multiple USB web cameras on your robot. So we'll talk about some of the details revolving vision systems in just a moment. And really, the last advanced sensor application that we're going to cover is odometry. Odometry has taken a big leap in FTC. Odometry basically means how can I find my robot's position on the field? And then using that information, how can I go to different points on the field? But if you're able to keep track of your robot's position on the field, if another robot just slams into you, or if you hit the sky bridge, it doesn't matter because your robot will know where it went and how it can still get to its target position. We're going to cover that in just a moment. But why don't we delve into vision systems? I'm just going to hide my webcam from you guys so you guys can see everything. Um, but again, computer vision is a huge component of autonomous sensing and scoring, and there are many options available for you guys for vision systems. You can use again the phone camera on that Android phone on your robot. You can use a lot of USB webcams, and to the biggest difficulty crossing the barrier for using Vision FTC is finding the right library that works for you. So I know I spent between 2 and 3 years trying to get really comfortable with Vision FTC. There weren't a lot of resources available to me to kind of learn from. I wasn't really savvy in OpenCV or computer vision, so I needed a really good starting point, and I had a lot of trouble finding that. And I think in today's state of FTC, there are a lot more resources available on how you can use OpenCV. DogeCV is a really great resource for starting points for FTC, and of course the Vuforia library. So in this year's FTC game, you can use either OpenCV, which is a open source library, computer vision library that allows you to do vision detection. You can identify different color objects, different sized objects, whatever you want to do. It's for object detection. Um, but Doge CV is a subset of that, I guess. It's a library developed for FTC teams. I was part of the development team for this, but they make easy ways for you to detect objects or complete vision tasks in each year's game. And in fact, if you scan this QR code right here, you guys can jump straight into a in-depth tutorial on how to use OpenCV, how to use Doge CV in your in your robot on your phone to be able to detect, for example, the sky stone this year. So our tutorials are game specific, and if you just scan this QR code right here or take a picture of it, just for future reference, you guys can really learn how to use vision to take your autonomous performance to the next level. And then, like I said before, you very key. They're an FTC partner or sponsor, so they're always going to be involved in the game. So it's always a great option to have going forward. And these libraries provide you with reliable vision object detection, which is of the utmost importance when it comes to autonomous. If you're not able to detect the sky stone correctly, you're losing 10 points right there because of that bonus you get for the sky stones. And 10 points is really hard to make up in teleop and endgame if you're down to another team. So it's really important to have that reliable vision detection. And OpenCV, DogeCV, and especially Vuforia in this year's game provide you that advantage. So go ahead, scan that QR code, take a picture of it. We're moving on to odometry. I'm going to spend a lot of time talking about this because this is probably the most important thing that I have personally done on my team. So I'm just going to cover a high level overview of robot odometry. So robot odometry calculates the position of the robot on the field at any point in time. And it does this by using an x, y, theta coordinate position. So your x, y, theta, um, it provides you three measurements. If you think of the FTC field as a two-dimensional field, your robot is just a point on that field. It has an x coordinate and it has a y coordinate, just like on a Cartesian graph. But then this theta coordinate is actually pretty important because your robot might know where it is on the field, but what direction is it facing in? Is it facing the building site? Is it facing the sky stones? You gotta be able to distinguish that. And so that theta, Greek letter meaning angle, is the third important key factor that odometry provides you. So you know where you are on the field and what direction you're facing. And that provides you a lot of options going forward to figure out what you want to do. And then you see the way odometry works is that it estimates the change in your robot's position over a very short time frame. So I know FTC, their loop cycles are, uh, it varies on teams depending on what you're doing in your autonomous program, but you're going between 50 milliseconds, 100 milliseconds. It's very short periods of time. So your robot's calculating how much it changes in position over that short period of time. It kind of accumulates that all together to constantly update your robot's position on the field. And the way that robot odometry works is that you generally you have three tracking wheels, or also two wheels plus an IMU or gyro sensor that keep track of your robot's position. So I'm just going to briefly explain that. Oh, whoops. I want to go back over here. So if this is our robot right over here, most teams that use odometry, they're going to have three wheels, three encoder wheels. Now, what do three encoder wheels mean? Well, this means that they're just they're not attached to any motors. They're just attached to your robot. So they're just kind of dragging along with your robot as your robot moves. Um, And that's an important feature about odometry because wheel slippage will not affect the measurements. This is a super critical advantage of odometry. And why do I say that? Well, that's because if your drive wheel slips, this wheel right over here, this wheel is not moving at all. Sorry, I should go back to my laser pointer. This wheel, it's not moving at all because the robot's not moving. It's not attached to a motor, so it's really going to enable the tracking wheels to measure the actual position of the robot and track its actual motion, opposed to if you're using motor encoders, the wheels are moving, but the robot's not moving. So the robot thinks it moved, but it didn't move in reality. So that's a common area. That's a really drastic improvement with odometry. But what I'm just going to quickly explain how odometry works. If you have let's say you have a mechanism drive, that's a good place to start. Your robot can move in any direction. So you need to have a wheel that is facing one direction. So we're going to call this just a vertical direction. And you have to have another wheel that's facing a horizontal direction. Because if your robot moves at a 90-degree angle, like a mechanism drive, if it strafes to the right, this wheel over here is not going to move, but this wheel will detect that motion. So you need both this wheel and this wheel right over here. But what's this third wheel for? You might be wondering. So the way odometry works is that it relies on the angle of the robot. So, like I said, you can use two wheels plus an IMU and gyro sensor, but I think the best way to go forward is if you have two wheels, you can actually calculate two things. If your robot turns, one wheel is going to be going forwards, one wheel is going to be going backwards. Based on that information, your robot can calculate that change in orientation. And also, when you're going forwards and backwards or strafing a little bit, these wheels should be moving about the exact same. But if there's a change in angle, change in orientation, the wheels are going to be different. And being able to reconcile or use those values of both of the wheels, that's really critical to having a very accurate odometry system. And that's kind of why you have those three wheels over there. So again, uh, we have three tracking wheels on the robot, if you can imagine that. Um, Either three wheels, or you can also use two wheels and a gyro sensor. Um, the two wheel and gyro sensor is more common amongst like tank drives, six-wheel drives, but I would still recommend going with the three wheels because this third wheel right over here is very critical to being able to detect motion in that side to side area. If your robot either gets pushed sideways or if you have a mechanism drive and your robot kind of just moves in that general direction on its own, just because it has that capability to move in any orientation, or sorry, any direction on the field. And the really key advantage of odometry is that it's extremely reliable. So imagine this is just a test I do, but if your robot is driving it wrong and you just you push it to the side. If you have normal encoders, that's not going to be able to recover from that because it doesn't know that it's moved sideways, right? Because you're using encoders on the motors. But odometry picks that up because these wheels are not attached to the robot. So it knows that its position has changed. It can automatically detect that and continue moving to that same point. So if I have a robot um, that starts over here and I want to get to this position right over here, I could be driving along this path right over here. But what if another robot hits me? I'm going to veer off to the side all of a sudden. If you have motor encoders, it might think that I just want to keep going straight like I was before. But odometry detects that your new point is right over here, and it's going to just draw up a new path and go straight back to that target position because the robot knows its position has changed, which is really the powerful thing about odometry. I'm just going to go ahead and erase all this ink on the slide. Um, and what our team did is we actually used odometry last year. And I think one of the great things that teams have told us, mentors and other teams, is that a couple years ago, you had a really top tier teams. Think gluten free. You had gluten free was up here. You had a top tier teams down here, and FTC here was everyone else. Last year, when we used odometry and figured out how powerful it was, how it could really improve your autonomous performance, we want to bring first of all, we want to bring that we want to close the gap between the higher tier teams and the rest of the FTC community. So we actually developed an odometry spell book, which is a series of 5 videos how you can build a drivetrain with odometry, how you can wire it up, and how you can get started programming. And in fact, we provide the code to you guys. We want you to be able to use odometry. We want everyone to be able to have that learning experience going forward. And it's really key because we want to bring everyone else up to those top tier teams. And so go ahead, scan this QR code, take a picture, take a look at it later. I know the season might be coming towards an end for some teams, but this is a really cool project you could work on during the summer, for example. Learn odometry, learn how to program. It has some really cool applications, and I'm actually going to talk about that right now. So, how can robots use odometry? So, I just talked about one way, which is that, whoops, I want a pen. If we're at point A and we want to go to point B, We know our position is right over here. The robot can calculate the path it needs to get to that point B, and it can drive along that path using odometry. But and it can recover from any direct hits. So if we take a hit, we're going along a path, we take a hit, we get pushed to the side. It knows it can just recorrect that path on its own since it's constantly updating its position, constantly knowing where it is on the field. That's a really cool feature, I think. It adds a lot of intelligence to the robot. But you can take it one step further. So we have different path planning algorithms. Now, what exactly is path planning? Path planning is figuring out how to get how to form your paths in some of the most efficient ways possible. So um, let's take an FTC field, for example. This year's game, for example. You have some barriers, right? You have your quarry over here on both sides of the field. And you have this sky bridge right over here in the middle of the field that's a giant obstacle with barriers on the side, right? That's plenty of places for robots to run into, which is not fun. So I want to talk about A-star search. That's a really key part of a really cool application of odometry. So let's say my robot's over here. I want to pull the foundation, which is I'm just going to say it's this line right over here, and I want to go over here and then go somewhere over here because I see a stone over here in autonomous. Well, there are two challenges to that. If my robot moves over here, if we go on a direct line, you can imagine this, we're just going to hit the sky bridge. But it would be cool if I could find a way to navigate around this fixed obstacle that is the sky bridge. Well, lucky for you, A-star search is the perfect place to start for that. Because what A-star search does is if you give it a kind of a grid or a graph of areas you can go and areas you don't want to go, the robot can automatically calculate the most efficient way to get there. So let's say my robot is right over here. I'm the star and I want to go to the circle. But let's say that there is an obstacle right over here and right over here. Now, if you're just using odometry on its own with a point A to point B kind of space, it's going to want to think to go right over here, but you're going to run straight into this obstacle. And while your robot knows it ran into the obstacle, it can't really do anything about it, right? But what we want to do is we want to be able to navigate around obstacles, which is why A-star search, what it does is it explores all possible paths and figures out the most efficient path to go on. It's very similar to Dijkstra's algorithm, if you know that from maybe a computer science or programming class. But what it would do is it tries possible algorithm or paths. So it could try this path, but again, it runs into a no go zone. It could try this path, but again, it ran into this zone right over here. And after trying a bunch of different paths, it's going to know that the most efficient path, and in this case, the only path to your target position, is to take this L shape right over here to kind of go along this direction. So that's just one way of using A-star search. We developed that for a robot this year, and it was super cool how the robot's just kind of able to go around a variety of different obstacles. And what you can do is, if you take the FTC field, for example, sorry about this. If you take the FTC field, divide it up into a grid, and just say, I can't go here, I can't go here, I can't go here, but you can go in all these other places. I'm just making more grids for myself. But you can go in all these other places. The robot can figure out if it's over here, I want to go over here, I'll just take this path. That seems like that's the most efficient. So you want to be able to use A-star search to be able to do that. And that's, I think, a really cool step from odometry. You figure out how to move to point A to point B, but how do you navigate intelligently? That's a really important aspect to this. All right. Odometry also enables you to use a peer pursuit controller. I'm guessing most of you guys aren't familiar with the peer pursuit controller, so I'm going to go a high level overview. So let's say using odometry that I'm starting over here, I want to go over here, and then finally go over here. You could do an abrupt motion, something like this, where you go point A, point B, point C. but that might not be the most efficient way. And what happens if I'm starting facing this orientation, but I want to end up facing this orientation? Am I gonna have to move, do a pivot, then move again? Am I gonna move, and then pivot again? It can be a little complex, and it can also be a little inefficient. Because keep in mind, any robot, the best way it moves is if it's facing in the forward direction. So if you want to be going as fast as possible, you always want to be moving in that forward direction. And what kind of pure pursuit enables you to do is, I want to draw it in green over here, but it enables you to go to this point, but then you realize I need to go to the next point. So it starts turning. It does a curve motion and it gets to that target position. And the way it does this is you can think about the robot as a circle, and it's constantly finding intersections of the line, and it's looking ahead to the next point. But over here, if I draw a circle, I don't I intersect with this point next, right? So I want to go from this point to this point, bypassing this point right over here. You can see the radius of this circle enables that. So you kind of want to that kind of idea or those calculations creates that curved motion that you follow to your next point, which is really cool. It's kind of like a car driving, if you can think about that. You're doing turns, not pivots. It actually really speeds up your efficiency, which is really important for really quick and fast autonomous performance. If you think about some of the teams this year, gluten free, Cubics, some of the other really high level teams, they use this kind of stuff to be able to move quickly across the field. Because getting 5 stones or 4 stones in autonomous, it requires lightning fast motion, and you have to be able to get that, which is why Peer Pursuit is a cool extension of odometry, which is something you need, first of all, before you head on to Peer Pursuit. And the last thing I'm not going to talk about too much because I personally don't have too much experience with it, is the Roadrunner Path Planning Library. Um, this allows you to plan out trajectories, do really neat curves, splines, that kind of stuff. Um, there are some resources available online. There's awesome documentation, but that's something you can use if you have odometry and you want to be able to kind of do cool curves, navigate really fast on the field. Explore using the Roadrunner Path Planning Library. It's really useful for FTC teams. Allows you to do some really cool motion profiling. And yeah, so those are some kind of extensions of Odometry 3 examples of implementing intelligent path planning algorithms. And like I said, I really want you guys to be able to do this on your robot because it's an amazing learning experience. Being able to apply this in a competition setting and take your robot to a competition, knowing that it's the smartest robot on the field that can really do autonomous really well. So I really want you guys to check out this spell book. It's got 5 videos again, so that I can walk you through step by step for getting odometry up and running on your robot. And it's actually a much more simple process. I'm going to remove my webcam so you guys can scan the code. I just realized my webcam was covering it. But you guys can do that right over here. And most teams just use odometry in autonomous, but you can actually use it in teleop as well. I'm just thinking in this year's game, imagine being able to drive across the field and go to the position you're stacking blocks autonomously. You can do that with odometry because drivers take a lot. There's some bad drivers out in FTC. I know that our team is not the best at driving, which is why we use a lot of these automated enhancements to go from maybe say the sky bridge to the stack we're stacking on the stones. And this way, you eliminate the time you're lining up. It's a lot quicker than a human driving it. Robots are a lot better doing things themselves than humans are. That's just a reality. And you can use odometry and teleop for automated driver enhancements to kind of really speed up your performance, make things a lot better, take your team to the next level. So hopefully that gave you some ideas on how your team can implement and use odometry um, on your robot. Whoops, I accidentally changed this slide. Sorry about that. Um, yeah, so hopefully you guys are able to learn from that. It's really key to be able to, once you use odometry, how can I take it to the next step? So these videos will walk you through getting odometry, and there are lots of online resources for kind of advancing to A-star search, peer pursuit, and using the Roadrunner path planning library. Um, And then the last thing I want to talk about, it's kind of an extension off of odometry and that kind of automated driver enhancements we talked about, is kind of bringing together a bunch of different sensors and combining the different sensors for greater consistency and driver enhancements. So let me just think about some common mechanisms. So this year we have an intake. What if the intake automatically turned on when a stone was in front of it? Well, guess what? Sensors enable you to do that. What if your driver forgets to turn on the intake? You're going to waste time trying to realize that your intake is not on. You can bring together different sensors, like maybe some distance sensors, ultrasonic sensors, color sensors, to detect when a stone is in front of the robot. And maybe if you have a active intake, a wheeled intake, those will automatically turn on. That way, if your driver forgets, or if your driver is preoccupied with something else going on the field, the robot can take care of some of those human errors that are happening. So sensors are very important for implementing driver enhancements, and using sensors can drastically speed up performance and scoring in teleop. If the driver doesn't have to do everything and the robot can help out the driver along in the process, the driver just has to go from point A to point B, press a couple buttons, and you're done. You don't have to worry about controlling complex mechanisms. For example, difficult operational tasks can be drastically simplified. If you have an arm that's moving in like 3 or 4 degrees of freedom with a wrist or a claw or something, that's a lot of buttons on a gamepad. And that's really difficult for a driver to control. Using motor encoders, using advanced trig on your calculations off gamepad inputs can really simplify the process. You want your robot to do thinking in teleop, not just in autonomous. In autonomous, it has to be able to do everything on its own. In teleop, you have the option, you could say, of adding a driver. But really, if you can automate as much stuff as possible, your robot's going to be really quick and really fast and really high scoring. And you guys are going to kind of take that robot performance to the next level. And perhaps one of the more important thing is that sensors can correct human errors. Another application of sensors in this year's game for driver enhancements is if your robot can detect if it has two stones. Let's say I have a distance sensor right over here and a distance sensor right over here, and there's a stone in both locations. I know the robot will have a stone. I know the robot has two stones, and I can just start ejecting them. I can spit out the stones. Um, that will correct the human error on the driver. It will help you score faster, and it will help you from accumulating penalty points, which is obviously important if you want to win a match. So that's just something to think about. And I actually have a pretty cool thing right up over here, a video from 2 years ago. This is a robot from 2 years ago. I'm going to switch off my webcam so you guys can see what's going on. But I'm just going to start the video, and you'll see. I'm just going to walk you through some things that the robot's doing. So if this video will start. Oh, it looks like we are having some problems. I'm just gonna take a quick look. I'll just show you guys it like this. But if I play the video, you're gonna see the wheels turn on to intake the block. Now, what happened automatically was the wheels stopped, the lights turned on, and the lift came up. Now, why are those three things important? The lights let the well, first of all, the wheels stop. This prevents us from damaging the block because the drivers might not be able to see when we have a block, and won't know to turn off the intake. Sensors automatically do this for us. And if I rewind this just a little bit, you can see there's one sensor over here, and there's another sensor back behind this block. So you can detect those two blocks. And my next point is if the driver can't see if we have a block or not, these LEDs right over here tell the driver that. So once the block is in, the LEDs turn on, drivers know they're good to go. They can start driving away from the pit and go to stack those blocks. This is from 2 years ago, just for you guys who don't know the game from 2 years ago. But what's another interesting thing is once the block comes in, I'll play that clip again. Once the block comes in, the lift automatically goes up, which means that the drivers aren't dragging anything on the ground, which is a pretty cool feature. Because the driver might not be able to react in real time as fast as the robot can, since it has sensors to do that. So that's just a really cool aspect of the driver controlled features. And in fact, in the year we developed this robot, we actually had our whole mechanism flip so we could pick up two stones on top of each other. And if you think about that, if a driver's doing that on his own, what does he have to do? He has to lift the lift, he has to spin that servo, and he has to come back down. That's a lot of processes. You can make errors that cause hardware damage and some wiring issues. It's a lot easier for the robot to do that on its own. So what we actually did was using the motor encoder on our lift, again another sensor and the color sensors. All the driver has to do is press one button. All the driver has to do is just press one button. You It automatically lifts it up. It flips it. It comes back down. You need sensors to be able to do that on your robot. And I think I'll just play this clip again while I talk. But using sensors, this is just one example. There were 20 sensors on this robot, and being able to use those sensors to help the drivers is a really critical component, just as important as autonomous. Because if you can score really fast in autonomous, or sorry, if you can score really fast in teleop, it provides a huge advantage to your team going forward. And I think that being able to bring together those different sensors, kind of sensor fusion, the concept of combining different sensors, will give you greater consistency. It will give you redundancy, but it will also make it a lot easier to drive your robot. Robots are complicated machines. They can be very difficult for humans to operate. Sensors will help it make it easier for that. There are lots of ways. I'm sure you guys can brainstorm different ways for your robot to do things like that. But sensors allow you to correct for human errors. They automate processes, make it a lot easier for your robot to go along. But yeah, that's about it that I have for you guys. Oh, of course, the video plays now. But hopefully you're able to gain a lot out of this presentation. Um, Hopefully you were able to understand some of the ways you can program in FTC, the power of block programming. I cannot stress that enough. It transformed how our team operates. I suggest you guys do the same. Go back, take a look at that QR code, take a look at those videos. But the power of block programming, and then moving on to some of the advanced things in FTC, odometry, vision, advanced path planning algorithms, libraries like OpenCV, DodeCV, Roadrunner. Those are really great ways for you guys to take your robot to the next level. How you can really elevate your programming and your software. Um, Before we end, I just want to take a chance to thank some of Wizards.exe's gold sponsors: Lockheed Martin, BAE Systems, Abbott, and Pepco. These companies really make our team's operation possible. I wouldn't be here giving you this presentation. We wouldn't be able to develop our awesome video series that you guys should check out without these incredible sponsors. Um, so I just want to give a quick shout out to them. And thank you guys for watching. I just want to give a shout out to the organizers of the World Shop International FTC Conference. It was an amazing experience being able to share some of my experiences with you guys and introduce some really advanced and seemingly intimidating concepts that can take your programming to the next level. But in reality, it's not that difficult once you really break it down and really dig in. And again, that's what our videos will help you do. I'm just going to go back in the presentation. If you want to take a look at our block programming spell book, scan the QR code right over here. I'll leave this up for a few seconds. Scan the QR code if you want to check out our awesome videos. We have our Vision Spellbook series. It'll teach you how to use DodeCV, OpenCV, and Vuforia, all in this year's game. Take a look if that interests you. And of course, Odometry. We have a 5-part video series to highlight the key aspects of Odometry, how to get it up and running, how to program it, everything. So take a look at that. And yeah, so thank you guys for listening to this presentation. I hope you were able to gain something out of it, whether it was the importance of sensors, how you can think about using odometry on your robot, just how to think about using different sensors. Hopefully, you were able to gain some of that, and I hope that you guys are able to implement that on your own robot, whether it's for this season or seasons in the future. I know that we're ready to take questions now, so hopefully you guys were following along. If you have any questions, we'll be happy to answer them. If you have any questions following the after this conference, you can contact us at wizards.exe at gmail.com. You can reach out to us on social media. You can look up our Twitter, Instagram, Facebook, whatever. And then you can also contact us on our website and just catch up on what our team is doing on our website as well. That's wizards-exe.weebly.com. Thank you guys so much for allowing me to share my expertise and experiences with you. And I hope that you were able to take a lot out of this presentation and apply it forward. Apply it on your robot in upcoming seasons. Again, thank you guys for listening. Hey guys, so that about wraps up the pre-recorded presentation. I'll just be monitoring the chat for the next few minutes if you guys have any questions. If you don't, I'll be ending the stream around 4 o'clock, 4:05, depending on how many questions we have. But I'll just wait around. There's a decent delay or latency, probably 20 to 30 seconds on the stream. So don't be surprised if it takes a little bit for me to get to your question. But if you have a question, just put it in the chat and I'll try and respond the best I can. So I just got a question about the different vision libraries available to teams, OpenCV, DodeCV, Vuforia. I think this is something that changes every season. I know in this particular season, I've personally found the most success with Vuforia. Um, it's easy to use. Vuforia is pretty easy to use, especially since it comes with the FTC package. It's pretty well documented, and it's developed for this your specific game. So So I think if I'm just talking about the Skystone season, Euphoria was the best way to go. But it's really up to you as a team. You have to, or as a programming team, you have to kind of experiment with your different options. I know in the beginning of this year, I spent some time working with OpenCV and Euphoria, as well as the Doge CV library. So that's just something that you have to kind of play around with. Um, if you are starting out with Vision, I'd recommend using Vuforia and then maybe watching or reading through some of the Doge CV documentation to kind of get you jump started into the OpenCV library. But if you're starting out, I recommend Vuforia, but I also say kind of play around with your options, see what you can learn from the resources available. Um, and to see what works out for your team and the best. And again, it depends on each year's game, but it's mostly a personal preference and kind of which option gives the best performance. All right, I just got a question about kind of giving a simple example of a curved line follow. I'm not sure if I can quickly do that on the video, but I'll try and explain some of kind of the basic principles and kind of the math behind it. I'm just going to switch over to this screen over here, and I'm just going to just draw something real quick for you to see. I'm not going to be able to go into too much detail just because of the nature of this, but say we're trying to follow, say we have 3 points. We're starting over here at point A. We want to go to point B, and then we want to go to point C. So this is specifically from the Pure Pursuit motion controller, where instead of going like this, point to point, which can be a little time consuming, what you'll want to do is kind of curve around that point B. And I'll show you some of the math that goes behind it. So we have point A, point B. You have to excuse the handwriting, and point C. Um, if we kind of make a projection, or we think about the path that we would go on. So we go from point to point, point to point, and let's say we're over here right now. What the robot would want to do is, if you imagine you draw a circle of some sort of radius, like this. As the robot moves, the circle stays on some sort of intersection of the line. And this is the point that the robot's trying to go to. So you can see if the robot's at this point where the red circle is, and you have a circle of this radius, this point is still on that same line. But then as you progress further down the line, so let's say we go over here, and we still have that same radius, roughly the same radius. You have to excuse my drawing. You notice that the intersection in front of the robot in the direction of motion is past point B. So what the robot's actually going to be doing is, instead of driving to point B, it's now going. Blue is a poor choice of colors. Um, but it's going to be driving to this intersection instead. So in reality, what happens is it's following along this line, but then over here it sees it intersects with the second line segment. So it kind of starts following the path over here, and then at this point it'll terminate the process. So it kind of creates that curved motion. We don't, in terms of a specific example using Java, we don't have that ready to release. But as I mentioned in the chat during the presentation, we're going to work on getting together a video for the Roadrunner path planning library, which helps you with all sorts of cool looking motions like spline curves, which kind of look like this a little bit. Multiple curves in the motion, or simple curves just kind of like this. So that's something we're going to look into developing. It'd be a kind of a larger video series, which may take some time to develop. But with the abrupt halt in the season, we're going to have some time to make those videos available to you. But yeah, I'm going to take a look at this next question in the chat. Do I recommend double Omni or single Omni? I think personally I would go with the double Omni wheels. For kind of two specific reasons. It gives you, so when you're calculating your forward motion component. Let me switch over to the screen where I can draw on again. When you switch over to this motion, whoops. Let me get the pen up. If you're moving in this direction, you're going to be able to. You have one wheel facing like this. But if you have a second wheel, what you can do is you can make sure that they're kind of returning the same values. You'll be able to average them out or account for any error. So I think that's the best way to go. And so I like the double Omni idea. Also, if you have issues with IMU drift, I think it's better to use the two odometry wheels to calculate your angle, which is something that you have to do in odometry in order to get an x, y, theta coordinate. So I think overall the double Omni provides better results. If you don't have the budget, or your design doesn't allow you to do the two Omni wheels, single Omni is perfectly fine. You might have to rely on your gyro sensor a lot more than you may want to. But in terms of moving from point to point and getting a reliable x, y theta coordinate position, there's not too much of a trade-off between the single and double omni for odometry. All right. Just gotta read this next question over here. How do you handle the impact of lighting conditions on object detection? That's a great question. So, in this year's game, we had a lot of problems in the beginning of the year, kind of getting a good read on that vision target because the Skystone target was black, right, for the most part. So if you're using Vuforia, um, it's hard to get reliable results and identify those key features on the target, and which is obviously very important. So there are a couple things you can do. The three things that's off the top of my head. You can use the phone camera flash if you're using your phone camera or your phone's kind of near your webcam, just in general. You can use the optical zoom feature on an Android phone. If you're again, this is only applies if you're using a phone camera, or if you have a webcam that supports the zoom feature. But those may be on the expensive side. But you can use the zoom feature on your Android phone, and you can also install an LED light strip on the side of your robot that's facing the Skystone or any vision target really. So if I think about what our team did this year is we actually did all three things. We used our phone camera just as a reference, but we turned on the flash. We zoomed in on the target and essentially cropped out all of the outside interference, so the phone was just focused on the target itself and its position in the camera frame. And then we had an LED light strip, a small one, maybe 8 inches, underneath our phone mount, so it would light up the whole quarry. That way, it would illuminate it and kind of brighten those features. So we actually have a video if you search through our YouTube channel. We have a video on using the flash and zooming feature of an Android phone. If you're using the Vuforia library, that is, in order to get a better detection. So that's something I recommend checking out on our YouTube channel. And if you still have problems with that, I would recommend you can use an LED light strip controlled by the Rev LED Blinken module, or a PWM output. That's just a simple hardware solution to the problem. But if you're looking to crop or zoom or flash, take a look at that video and it shows you how you can use the Vuforia library to your advantage. And I guess that's only helpful if you're using an Android phone. So if you another thing I recommend for getting reliable detection in different lighting conditions, if you get a higher end Android phone, we use the Nexus 5, but if you get one of the more recent Motorola phones, or a Samsung phone that has a really good camera quality, you'll be able to get good results from the zoom or auto focusing. Um, that's just a idea, but or a recommendation. But yeah, I consider the phone camera flash, zooming in, buying a webcam that can zoom in. That's also an option, or installing the LED light strip below that. But yeah. And for the cropping, if you use the zoom feature, it essentially just kind of targets in the middle. So you are essentially just cropping out the edges. I guess it's kind of it just zooms it in. So you're cropping out the top, bottom, left, and right equally as you zoom in more and more. Um, And then if you do use the Doge CV library, they do support features to crop the image it analyzes. So you can give a custom, I believe it's a pixel size, you can frame size that you give. You can give it a custom area to look at. That way you're kind of getting rid of everything on the side. So if you're using Doge CV, you have that more custom option. But if you're just using Vuforia, it just kind of the zooming in the center, I guess, perfect zoom as you described it, um, kind of keeps everything out on the sides. Yeah, no problem. So for preventing glare, that's not something we had to proactively do in this year's game. I know there are yeah, for if you're using LEDs or a flashlight, you have kind of to balance the intensity of that. That's one option. Um, I know if you're using an LED strip, you can tune with the Rev LED blinking. That'll reduce the light and the glare on the target, but you just kind of have to configure the settings that are just right for your robot, I guess. Some of the cameras that you can use on Android phone, they kind of adjust for brightness. So if you think about it, like I imagine if you just take out your phone right here and you focus on different targets, um, and you just kind of tap on different areas of the screen, it automatically reduces the light and focuses on that one area. So that's something your phone camera might do automatically. Or if you buy a webcam that has an autofocusing feature, that's something it could do automatically. But I think the main area with glare. So you kind of have to balance between the darkness that you have around the target in general and the glare. You just have to provide the right amount of light. Um, I know if you zoom in, if you keep zooming in, if you provide a lot of light, that can help the glare sometimes because you get a better look at the key features on the target. Um, but yeah, it's a little finicky. If you use OpenCV or DogeCV, you can play around with the brightness. Um, That's yeah, you can play around with the brightness of the image and look for solid colors and kind of filter out any saturation. Just look at the hue value, which is the pure value of the color, in terms of HSV, which is kind of like RGB, except it factors in the saturation of the color, which includes the glare. So I would recommend, yeah, you just have to play around with it a lot. That's what vision detection FTC is mostly like. You have to play around with the different settings that are available to you. But if you have the ability to control how much light you're shining or how far you're zoomed in, play around with those settings, and I think you'll find that something works well. If not, consider upgrading your phone camera to one of those to a camera that has a lot of automated features like the automatic focusing. But yeah. It looks like the questions have died down a bit. So I think I'm going to wrap up the presentation here. But if you guys have any questions, please feel free to reach out to our team at wizards.exe at gmail.com. We have a contact form on our website at wizards-exe.weebly.com. And you can also reach out to us on our social media, which I believe we've linked in the description below. I hope you guys were able to um, get your questions answered. Just learn a little bit about how you can use your programming to take your robot and your robot performance to the next level. Again, thanks for allowing me to share my experiences and some of my experiences with you guys. Again, if you have any questions, please feel free to reach out to us. Thanks for watching this presentation and participating in the Q&A, and that's a wrap.